Now let's look at 2024 F equals MA problem 25. This problem tells us that we have a yo-yo, right? So it's a rigid body because it consists of some massive uniform disks of radius r. Okay. But the interesting thing here is axle. So it's wrapped with string whose thickness cannot be ignored. So the problem says that initially, so once we wrap the axle with the thick string, so it is in such a relative position. So basically here, the radius here is the same as the radius of the uniform disk. And then we release it, right? So after we release it, basically the string is unfolded, right? Because it has the thickness. So after a while, when it's sufficiently long, we know that, so this is the position of this yo-yo. So for two massive disks, they are still with radius r, right? But what about is, so this is r. And what about the string? The wrapped about its axle. So its radius keeps on shrinking, say it becomes smaller. And finally, once the entire string is fully unfolded, so small r becomes 0, right? Okay. So the problem asks us to analyze the acceleration of the yo-yo, how it evolves over time. Okay. So here's the thing, right? So it should have the acceleration in the downward direction because it's going down, right? And initially isn't at rest. So it should have a downward acceleration. And also, we notice that. So here, because let's look at horizontal displacement from this vertical line. So the initial horizontal displacement is capital R. And finally, it should be 0. So it has some small horizontal displacement, right? So this really depends on how you understand the problem. So suppose you insist on saying that, so there should be displacement or acceleration on both vertical and horizontal direction. So basically, you look at those choices, right? So it seems that none of them is correct. But since we assume that because the string actually, although it has thickness, but compared to the radius r here, so although that is not negligible, but it's much, much smaller. So if you make this approximation, then we know that, so the vertical acceleration is much, much bigger than the horizontal acceleration. So you can focus on the kind of vertical acceleration, okay? So in the rest of the analysis, let's focus on the vertical acceleration, okay? All right. And how do you characterize the position of the system, or which general coordinate we should use? So we can use this one as x to denote the length of the string that has been unfolded. And we know x has a direct connection with small r. How they're connected? Because the string has the thickness. So let's just look at a two-dimensional diagram. Say the thickness here, the width is called d. Okay. So we have the following fact. Let's look at the total area, including the unfolded string and those that are still wrapped. So the total area is equal to x times d plus pi small r squared. They should be equal to the initial area when the string is fully wrapped. It is equal to pi r squared. Okay, so this is one equation. And the next, let's write down another equation. That is the conservation of the system's energy. Okay. So at each point, the system's energy, what's the kinetic energy? Is equal to 1/2 of the mass times the square of its velocity of the center of mass, right? So that should be x dot squared plus the kinetic energy that comes from the rotation about the center of yo-yo. So that is given by I. This is the moment of inertia of yo-yo about the center of mass times the square of its angular velocity, omega squared, right? So the system total energy should be equal to the reduction, the loss of the gravitational potential energy. That is equal to mg times x. Okay? So now we need to write down I and omega. What is the moment of inertia about the yo-yo's center? Because the strings are massless, right? So we just need to look at those massive disks. So it is equal to a half of m times capital R squared. And what about the angular momentum, small omega? So once the string is unfolded, at the unfolding point, there's no sliding, no slippery, right? Therefore, we must have that x dot is equal to omega times small r. That shows that the velocity at this point is 0. There's no slippery. Okay? All right. So now what we need to do is to first put these three equations together and solve them jointly. And we put them together, we will see that we have this one, 1 plus is equal to this one. Okay? All right. And for this one, we also recall that r squared can be obtained by applying the first equation. So let's plug it here. For this one, we will divide both sides by m. We get a half of x dot squared, 1 plus small r squared is equal to big R squared minus xd divided by pi. Okay? All right. And next, we can get this is equal to 2gx divided by 1 plus 1 half this one. Now let's simplify the right hand side. So first, let's multiply both the numerator and denominator by 2. Then the numerator becomes 4. The denominator becomes 2 plus this guy. Okay? And then let me multiply the numerator and denominator of the right hand side by the denominator on the denominator. So we get 4gx times r squared pi minus xd divided by 3r squared pi minus 2xd. Okay? All right. So now we want to get a closed form for x double dots, the acceleration, not for x dot. So we can do it by taking the derivative with respect to time on both sides of the equation. Then the left-hand side becomes 2x dot x double dots. And for the right-hand side, so we have to take the derivative of the whole thing here. So let me call this the whole thing over dx times dx over dt. Then we realize that x dot appears on both sides of the equation, so they cancel out. Then we get a closed form for x double dots that can be expressed purely in terms of x rather than x dot. So what we need to do next is to compute the derivative of the whole term in a green circle with respect to x. So now let's do some simplification, okay? First, we observe that both the numerator and the denominator have r squared pi. So let me simply set to be something called a, okay, to lighten our notation. And then we also observe that x and d come together. So why don't I set them as a new variable called 1? So x becomes y over d. Okay, so we get this expression. Then for its derivative, so we can take the derivative with respect to 1. And then dy over dx. So this is simply equal to d. Okay, so now the problem boils down to compute the derivative of the expression in the green circle with respect to 1. So let's do it, okay? So first, let me write down the x double dots in the explicit form is equal to d over 2 times d, the whole thing, over d1, okay? So what is the derivative? So we have constant factor 4g over d. Let me check it out. Times d over dy. So this guy is equal to, the numerator is y times a minus y divided by 3a minus 2y. So the term ahead of the derivative can be simplified as 2g. What about the derivative of this expression? Okay, so if you look at this problem, it just asks you to figure out whether the separation is always upward or downward. So which means that you just need to quantitatively check whether this derivative is always positive, or it is always negative, or a sign keeps on changing, right? But here for the training purpose, so I will give you the closed form. And then after getting the closed form, we can easily see for what y, the derivative is positive, for what y, the derivative is negative, okay? All right, so let's do the derivative. It's not too hard. So we can do it, complete doing it in just a few seconds, okay? So it is equal to this one. Then times the derivative of the numerator is equal to a minus 2y minus times the derivative of the denominator is equal to -2. Okay. So now let's reorganize the numerator and see what it looks like. First, for the coefficient for y squared, is 2y squared. Then let's look at the coefficient for the cross term a times 1. Next, let's look at the coefficient for a squared. So this is expression. So next, we need to check whether this term in particular, because the denominator is always positive, so we need to check whether the numerator, this one, is positive or is negative. So recall that we set y to be equal to x times d. So when the string starts to be released, right? So y starts to take the value from 0. And what is the terminating condition? So that is, the string is fully unfolded, which means that x times d should be equal to r squared times pi. So basically, we need to vary y from 0 up to a. Okay. And let's see how the sign of the yellow term changes. So for y that is very close to 0, it's obvious that the yellow term is pretty close to 3a squared. So it is positive. And when y is pretty close to a, then it becomes 2a squared minus 6a squared plus 3a squared. So this is very close to negative a squared. So it's negative. So it tells us that for the entire motion, for the acceleration, so initially, the vertical acceleration is in the downward direction. And when the string is pretty close to be fully unfolded, then the vertical acceleration goes up. Okay? So by observing this fact, now we know which answer is correct. So we should select B.